Oh, hopefully it's going smooth now. Let me just write down our title for today. Okay, good afternoon, and welcome everyone to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kaur, and thank you for tuning in on our second to last lecture. Good afternoon. It's glad to see everyone here. And let me just tune the video just a second. Let's try this. Yes, it is Friday. And hopefully you'll enjoy the weekend. So like I said, that this is our second last lecture. We'll have one last one on Tuesday. And you don't want to miss that one. And for that, we'll talk about the final exam, what to expect on it, what kind of the format it is. If you'd like, I can go over a previous exam. What do you think in the chat? The people that are here. We could go over some solutions. It will still be recorded, yes. Yeah. Yeah. It will be recorded. Okay. Okay, so if people think that's helpful, we'll do it. And again, send me questions. To cover. Maybe perhaps I might send you something else like a video if there's something for clarification. So maybe we might not cover everything, but I will try to send, if you do send me a question by email, I'll at least point you to a resource. Okay. So, like I said, lecture 33, the penultimate lecture. We're doing examples in the binomial distribution. So again, let's recall what the binomial distribution was. It's probably something that you should put on your cheat sheet if you're going to. We're going to have a one sheet of paper. You can have two sides where you'll have your cheat sheet, and maybe this might be something you want to put on your binomial distribution. So with the binomial distribution, there's three things that we need to have. There needs to be a success or a failure. The trials are independent. And the trials are identical. And that means something along the lines of, you know, if you're flipping a coin, it's going to be a coin flip for each trial. It doesn't go, we flip a coin, then pick a ball out of an urn, and then draw a card out of a deck of cards and then spin something on the roulette wheel, you know, the trials are identical. And we have what the probability associated with x. So if x is a binomial, binomial, random variable, and this is the little x is the number of successes, well, over here we have the probability of success, which was p, and that happens x times, which means that if we have n is the number of trials, so if you have x many that are successes, then you would have 1 minus p, or the complement, and you would have out of the n trials n minus x for the failures. And again, we could have arrangements like we had with the where we had when we were rolling, we had 4 rolls of a die, and we wanted to have a 6 was considered a success. Well, we could have 3 of them, but we also have the arrangements of it, right? So how many combinations are there for that? So you have n trials, and you're going to pick x of them. And that's it. That's the formula for the binomial distribution. And that is for all x from 0, 1, 2, all the way up to n. We also have the expected value, which was the number of trials times the probability of success, and the variance was the number of trials times the probability of success times the probability of failure. So we can say that x follows a binomial distribution, and we have a shorthand for this. So this is what, oops, let me just put this. So x follows, so this is a random variable. So it follows, and we use like a b to stand for binomial. And there's 2 things that we need for a binomial distribution. There's only 2 parameters. There's n and there's p. So it follows. This means a binomial distribution. That's the number of trials. And over here, that's the probability of success. And those are just 2 parameters. So to do a binomial distribution, what you could say is that the random variable x follows a binomial distribution. And with the two parameters, so let's say P is 1/3 and the number of trials, let's say, is 10. You could write this in mathematical notation as x follows a binomial distribution with, and now we're going to make sure we put in the right order. So we say 10 trials, and there are, with a success of 1/3. And the probability distribution P of x equals little x. So what we can do is we use our formula that we have up here. So we know that our n is 10, so it's 10 choose x times the probability of success, which is 1/3, to the x. And lastly, then it would be 1 minus p, so 1 minus 1/3 gives me 2/3. And n is still 10, so 10 minus x. And that's for x from 0, 1, 2, all the way up to, so in this case it's 10. So there we go. Okay, then the next thing that we can do let me just grab some more paper. The other thing that we can do is the expected value then. Of this random variable x. So that's NP, or so we know that there's 10 trials and there's 1/3 probability of success, so that's 10/3. And the variance so that's 10 times 1/3 times 2/3. So this gives us 10 times 2 is 20 over 9. So just with this little bit of information here, that x follows a binomial with 10 trials and a success probability of 1/3, it tells me a lot. I can generate the probability distribution, I can generate the expected value, and I can generate the variance very quickly. Okay, so we've done things like coin tosses before. Let's do an example where and this is just from the textbook. Here's exercise 10.2.5. And it says that the probability that a marksman misses his target on any given shot is 0.10. So there's someone hits a target. With probability 0.1. Okay, let's say if he shoots six times, what is the probability that he missed 2 or more times? Okay, so again, this would follow a binomial distribution quite easily because we can define a success or a failure. We're going to assume that the bullets are independent, or the shots are independent, and the trials are identical. So again, so assuming that the shots are independent, let x be the random variable of shots Now this one says if he shoots 6 times, what is the probability that he missed 2 or more times? So what I'm going to do here is I'm going to let x be the random variable of shots that he misses. And this is what we're going to consider the success. And that means, what's the probability of success in this case? What do you think in the chat? .9. Yes, exactly. Okay. Somebody wrote sad face. Somebody wrote, oh yes, so that was, so it's 0.9. And so then his failure would be 0.1. And the other thing that we have here is 6 times. So there's my p, and I know that n equals 6. So let x be a random variable. So I'm going to say that x follows a binomial distribution that has 6 trials, and the probability of success, or that he misses, is 0.9. Okay, so with that, what I need to do is come up with the probability of x greater than or equal to 2. So one way that you could do it is you'd calculate the probability for x equals 3 plus the probability x equals 4 plus the probability of x equals 5 plus the probability that x equals 6. And that can take a while. Or what we could do, oh, and I also need to have plus the probability of x equals 2. Right, because it includes 2. So 2, 3, 4, 5, 6. That's a lot of calculations. Or what we could do instead is the indirect method. So we take 1 minus the probability of x less than 2. And that means I could have the probability of x equals 0 plus the probability of x equals 1. Oh, maybe I should write out, here we go, just the generic version of this. So let's just write out the probability distribution for that. That's 6 choose x times the probability of success, 0.9, to the x times 0.1 to the 6 minus x. So that means then for p equals 0, that's 6 choose 0 times 0.9 to the 0 times 0.1, and 6 minus 0 is 6. Why x equals x? Oh, yeah, this is a capital X. So that's like big X equals a little version of x. Now let me try to remember all these. So here I'm just drawing out Pascal's triangle. Oh, sorry, you're right. That should be 1. That's a good catch, thank you. Okay, so I have all those. So 6 choose 0, that's just 1. 0.9 to the 0 is 1. And 0.1 to the 6 is a really small number. Two, 3, 4, 5, 6. And over here, oh, did I do something incorrectly? So 0.1 to the 6. 2, 3, 4, 5, 6. Yeah, no, it should be okay. And over here is 6 times 0.9 times 0.0. 1, 2, 3, 4, 5. So I have 0.00001 times 0.9 times 6. So it's a really small number again. And so that's all that you end up subtracting. 1 minus this really small number. 2, 3, 4, 5, 6. Oops. And I will double check just to make sure that I'm doing this right. Times 0.9, oops, 0.09 times 0.1, 2, 3, 4, 5. So it's quite a large probability that he is going to miss 2 or more shots. Am I missing a 0? I'm not sure. Does somebody want to double check that? Yes, I added 1 right here. Four, 5. Let me just double check. 1, 2, 3, 4, 5. Oh, did I? Okay. It everyone's writing oh in the chat. So what? What's everyone saying? Should I have left it or? Okay. Okay, what's the next one that we were going to do? Okay, so we did that one. Let's do something a little bit easier. If you fire 6 shots, what does he expect? Okay, so let's say that again. Let's use, maybe I'll use y just to make sure it's a little bit different. We're going to say that it's a binomial. We're going to say he has 6 shots, and we're going to say that the probability of success is 0.1. The expected value of this is 0.6. So he expects to hit 0.6 shots out of 6. Less than 1. That's not very good. We can do other things too, like here's another example. We have like a business. So let's say that probability of a business person canceling a reservation at a particular hotel is, we'll say, 0.4. let's say that there are 5 reservations. By business people. How many reservations does the hotel expect to keep? Okay, so again, from the hotel's perspective, we could model this using a binomial distribution. So let's say that let x be a binomial distribution. So we'll say it's a b. And we'll say that there are 5 reservations. And in this case, how many reservations does the hotel expect to keep? So keeping the reservation is the success. So then we would say that the probability is not 0.4, which is where they cancel, but 0.6, where they actually do keep it. So we'll say 0.6. And right here is the keyword expectation, right? Expect to keep. This is a quick calculation, so n times p. So 5 times 0.6. So 5 times 6 is 30. Move the decimal place over by 1. So you get 3. So the hotel expects to keep 3 out of the 5 reservations. Is everyone okay with that? It all depends on how you set up. Can the exam just be a bunch of... I wish. But it all comes down to how you set up the problem. So this is one way I've done it. You know, this is kind of A. You know, if I had done how many they expect to lose. So again, kind of keeping with the original, you could just say let y be a binomial distribution. We'll say that again there's 5 reservations. In this case it's 0.4, which is, that's what we're going to call the success, which is to lose your reservation. Then the expectation, expected value of y, is 5 times 0.4, which is 20, and we move the decimal place, so it's 1. So there again, so the hotel expects to lose 2 out of the 5. The exam is not opinion-based. The exam is problem-solving based. So this was page 3. Okay, what's the next one that we can do? Another thing that you can model here's something very similar. It's like 10.2.6. Something like which is with quality control or quality assurance. We'll say something like we know that 30% of computer chips are defective. And this is from a particular machine. Okay. So you can let's go A. Let's say that find the probability that out of 5 chips, exactly 3 are defective. So here is where we have 5 chips. This is kind of the number of trials here. That's our n. So n equals 5. We'll say that find the probability that out of defective. So this is what we'll consider our success. And we know that the probability then of that is 0.3. So we know that the formula for this should have the form 5 choose x times the probability of success times the probability of failure. So in this case it would be that the chip actually works. So there's 5 minus x. So over here, so again, this is a binomial. We'll say x, so it follows the binomial. There's 5 trials, and it's got a 0.3 probability of success. So we want to find that exactly 3 are defective. So its probability of x equals 3. So 5 choose 3. So we can calculate this. 5 choose 3, so that's 5 factorial over 3 factorial minus 5 minus 3 factorial. So 5 over 2. So that leaves us with 10. So I have 10 times, so over here I have 3, and that's cubed, so that's 27, so 3 cubed is 27. And then I need to move the decimal place 3 times. 1, 2, so 1, 2, 3. And over here it's 7 cubed, so that's 49. I need to move the decimal place twice, so 1 twice. The nice thing about that is with multiplying that by 10, I can move that decimal place, so I get 0.27 times 0.49. And I can do okay. Good. I beat somebody in the chat. Excellent. So I got 0.1323. So that's the probability. Let's just do one more question just before we wrap up. So what's the number, expected number of defective chips? In 5 chips. So again, we can keep our binomial random variable. So again, I'll just kind of write this out for completeness. There's 5 chips or 5 trials, and the defectiveness is 0.3. So we have an expected value of 5 times 0.3, which is 5. I was about to say 15, but 5 times 3 is 15, and I move the decimal place by 1, so that gives me 1.5. So we expect 1.5 out of 5 chips to be defective. Okay. Thank you everyone for tuning in on this Friday afternoon. My name is Richard Kohar. If you have any further questions, feel free to send me an email at my RMC email address. You know that email address, as well as tune in for that Tuesday class, and we'll be wrapping up this course. Thank you everyone, and have a great weekend.